Okay, there was no sound on the. I was going to say Cyclops, but on the Cycloid. So this time with sound, and wow, look at that glare. Is that from that? At any rate, I will now do it with sound. Um, the Cycloid. So the cycloid, as you recall, is what you get when you take a wheel and it rolls along the ground, and you pick a point on the wheel and you follow its path through space. And so the book uses the example of the ant on the wheel. Not sure I'm completely stoked about that, but here was the deal. The derivation in the textbook for the cycloid was very quick and very slick, but not intuitive, not obvious. And it seemed so. This is a judgment call that when you're doing mathematics, you have to make. Sometimes you can do a derivation or a proof and you can make it very short and abbreviated. I mean, that's good. Um, but it may possibly leave the reader wondering what the heck is going on. So, what I want to do is I want to derive the parametric equations for a cycloid, and I want to do it in what I would think of, or other people would think of, as a natural or intuitive way, which is to say, suppose you've never done this before. You've never done this before. It's the first time. How would you go about doing it? Oftentimes, the slick derivations or proofs is where it's not the first time you've done it several times, and then you've given some consideration on how to make the proof short. Hey, I'm going to have to say this several times. What the book does is correct. It's not wrong. And it's more of a stylistic or aesthetic difference in how you present the proof. Richard Feynman and this guy named Schwinger very famously had arguments over this, you know. But here's the cycloid. Here we go. So we have, there's the road, and here's the wheel. And let's say the wheel is of radius r, and the wheel is rolling on the ground. And maybe we think that we have a pen attached here. This is how these old spirograph toys used to work, more or less. You would actually take a pen or a pencil, and there was a little hole, and you would put it there, and you could roll the wheel along, and you could feel the curve being traced. So if you've never seen one of those, maybe just Google spirograph, and maybe you can still buy them. Maybe I'll buy one. I'll go online and buy one. Now, the first thing you have to consider is, what is the parameter? When you parameterize an equation, you have to have a parameter. Very often it's t, it's time. And I think that's a pretty legitimate parameter to choose for this one, because imagine the wheels like a wheel of a bicycle. It's going down the road. What would be the most natural thing to know would be the velocity, the linear velocity, how fast the bike is going down the road, and then how long it's been going down the road for. That seems to me to be the most obvious and natural setup. So let's say that we're given, maybe I'll write it up here. Suppose we're given r, we're given the radius, and we're given v. And by v, I mean the regular, ordinary linear velocity going down the road. Now, suppose the wheel is here, and it's gone down the road a ways. It's gone down the road a little bit. Now, this drawing is not the scale. I said that on the last video, but since there was no sound, you didn't hear it. Which is, you'll see what I mean by that in a second. But I want to try to make the image a little bit clearer. Let's suppose this point right here is now here. So I'll draw on this spoke. And again, that's the radius of the wheel. I would like you to, something, I mean, there's these interesting moments where all I can really do is say, hey, do you see what I mean? Or do you understand? Or do you follow what I've just written? Let me see if this makes this any better. A little experiment here with the light. That's not helping matters out. I'll try to avoid the magic glowing dot right here. Maybe I don't think we need this piece up there. Here's what I mean. You see this distance here from here to here? Let's call this d. That is the same as this arc length right there. Now, it doesn't look that way because of the way I drew the diagram. If I had drawn it more accurately, the problem is this wheel might be impinging on this first picture, and then it would make the diagram harder to follow. So you can decide that. But I'm going to call this here S for arc length. I don't know where that comes from, but you've probably seen that's a standard approach to writing arc length. So we know that S equals D. Now, I don't necessarily know where I'm heading, except to say this. Ultimately, what I want to find, this is now to be thought of as a generic point on the cycloid. So this generic point here, let's call it xy. We want to find x as a function of t and y as a function of t. Now, it won't be the same function. Oops. So this is what we're trying to find. This is what we're given. And when you do a problem like this at first, you won't necessarily know what to do. My way of looking at these a lot of times is if there's a tricky or ingenious thing that has to occur, maybe I better remember that or be prepared to struggle hard to figure it out. Other times you just do what seems to be obvious, and lo and behold, you will get the answer. And that's very common, especially for those of you going on mathematics further and further and further. That'll become a theme that you'll be aware of. Now, I noticed that S and D are the same, and I also know that the wheel would have turned through an angle theta. Now, I'm starting to get a lot of concepts. We have a length, we have an arc length, we have an angle, radius, a horizontal velocity. Part of me is thinking, oh man, I already did this whole video. Well, okay, so what? I'll do it again. Whenever you have wheels in motion, I think of this equation. Or here, I'll use a little r because I used a little r before. That equation is, you should know it, but if you don't know it, well, there it is. It gives you the relationship between the linear velocity, the angular velocity, w, omega, whatever, but this symbol, it's really supposed to be a Greek letter, and the radius of the wheel. Maybe we'll use this, maybe we won't, but if you have wheels in motion, velocity, spinning, you either want to be well aware of this or have this written down. So if need be, you can use it. While I'm thinking about it, whenever I have wheels in motion, we typically measure angular velocity in radians per second. Yeah, I mean, you could do it in revolutions per second or degrees per century, but almost always it's radians per second. And so you may want to recall the definition of radian measure. I mean, what is the definition of a radian? You should know. This is actually one of those things that if someone wakes you up in the middle of the night and says, quick, what's the definition of radian measure? You really should know. This is well worth knowing. So if you have if we have an angle, there's an angle. What is an angle? According to Euclid, an angle is which is subtended by two coterminal rays. It seems like it hardly explains anything, and yet that's really what an angle is. You take two rays, and the angle is, well, that thing. It's kind of interesting because if someone asks you to point to the angle, I'm not exactly sure what to point to. We all get it, but it's not really the area enclosed by these two rays, but sort of, I don't know, that's the angle. And we usually make this funny mark. It's just to call our attention to it. But what is the definition? Well, you take a circle and draw it about the angle so that the point of cotermination of the two rays is the center of the circle. And this arc length S, and that has a radius of R. And so this is S divided by R. Now, again, this is the definition. This is a theorem. You can prove this. But this is a definition. It's the definition of radian measure. You really want to have that in your minds pretty much anytime you need to access it. And one thing I see is, look at this picture over here. See, I see an angle, I see a radius, I see an arc length. And that's why I thought to bring this up. Now, again, what am I trying to do? I'm trying to find what the x and the y coordinates are. Well, one thing I know is the distance is equal to velocity times time. If we think of the wheel started rolling, ready, set, go. When we first start the stopwatch, sorry, I'm thinking about this. I don't know how, do they still make mechanical stopwatches? But so maybe ready, set, go, and you press the button. Look, the wheel starts here, and the wheel's going along the ground with a velocity of v, and so of course, well, v is d over t, so you solve for d and you get this right here. So this gives us d, so we know what d is. Now, think about what the x-coordinate is here. What's the x-coordinate? Well, it's d, but it's not quite as far as d. We actually are going to have to subtract that length. So we need to find that length and subtract it from D, and that will give us X. So what is this length? Well, I've got a nice right triangle up here, and I know this angle, this sort of upper, if you will, this upper angle right there. Let me just call this L. Oh no, is it visible? Well, oh boy. This length right here, this length, you can make a note of it on your own paper. I'm going to call this length lowercase l for L. So let's see if we can find L. Well, let's take a look at the picture. What comes to mind? I don't know, maybe sine of the angle. What's the definition of sine? Opposite over hypotenuse. So L is equal to R sine theta. Well, remember, I'm looking for X as a function of T. X is a function of T. Well, take a look at this. My attention is drawn to this right here. Multiply both sides by R, and you get S is equal to R theta. What was S? S was D. So VT equals R theta. So divide both sides by R, and you get VT divided by R. Here's theta as a function of time, and so we get little l is equal to R times sine of VT over R. So it's little l. Now what is X? X is D minus L. So let me go ahead and write that down. X is D minus L. What was D? I think I had it written down somewhere here. So X is equal to VT minus L is R. I don't know why the board's all squeaky. VT divided by R. There is the parametric, or the part of the there's the parametric equation for X. X is a function of T. Let's see if I can get this a little bit closer. I didn't mean to get so close to the camera there. Spooky, huh? At any rate, look, there's X, so there's success. It looks horrible, but think about the setup. It is kind of complicated, sine of a cycloid. Are we really expecting maybe a super simple example? But let's go ahead and find y. And then I want to show you maybe we can write this in a simpler way. Okay, so what about y? Well, let's see. What is y? Well, y would appear to be the radius minus. Now, maybe we're going to have some little difficulties with pluses and minuses, because if I had drawn my diagram where this point was up here, then it would be the radius plus a certain amount. But for right now, I need another letter to represent length. So L, I don't know, geez. What are these radius? R? I'll use A right here. So look at the picture. So y is going to be R, but then minus A. So R minus A. So let's see where I can write this, maybe down here. So y is equal to R minus A. Well, we got to find A. Well, let's go back up here, and we've got a nice little picture up here. So looking at that angle right there, maybe cosine. So cosine of theta is adjacent, cosine is adjacent over hypotenuse, so it's A over R. So A is equal to R cosine theta. Hey, that's not too bad. Look at this. Y is equal to R minus R cosine theta. Oh, but we want this as a function of T. So Y is equal to R minus R cosine of, and somewhere we had theta written down somewhere. I can't remember where. Oh, right here. VT over R. VT over R. And for fun, I'm going to factor out the R, because you already spent years and years and years of your life factoring things. So, is it visible down here? So Y is equal to R times 1 minus cosine of VT over R. And I'm going to put that in a box. Make sure that's visible on the screen. There, these are the parametric equations for the cycloid. Now, here's something that I'm going to keep saying. I said it on the first muted cycloid video, and I said it on the witch video, and now I'm saying, hopefully where you can hear it, and that's the following thing. We want to ask ourselves, does our answer make sense? Maybe more to the point, is our answer reasonable? And the way we do that is we pick a few selected physical moments where we know what X and Y should be, where we know what this point should be, and our equations had better produce that. because if they don't, we know the equation's wrong. If the equations agree with what we expect, that doesn't mean the equations are right. But if the equations don't agree with what we know, then we know the equations are wrong. We can throw them out. What would be a good place to start? Well, how about when t is 0? When t is 0, remember that's the origin. Or, well, you couldn't remember because the first video was muted, but that's supposed to be the origin. So what are the x and y coordinates of the origin? 0, 0. So when t is 0, x better be 0 and y better be 0. So let's look at our equations. If t is 0, that's 0. That's 0. What's sine of 0? 0. That's 0. So great. What about down here? If t is 0, all this is 0. What's cosine of 0? 1. 1 minus 1 is 0. That's 0. Okay. So now I'm going to do this. I'm going to make this a ritual from now on. I'm going to go, whew. Because again, if that didn't come out, then no matter how much work I put in this, too bad for me, all that's wrong. What would be another good moment? Well, honestly, a good moment would be to take a look at. I can think of two sort of obvious ones. One might be when theta is 90 degrees. I don't know if that's a good one to look at or not, but when theta is 90 degrees, if theta is, here, I'll even do it in degrees, pi over 2 radians, right? But 90 degrees, then what would I know? Well, I would immediately know that y was a, right? Because when theta is at 90 degrees, we're over here. So we know y right away. Let's check that out. When theta is 90 degrees, remember, look at this right here. This Vt over r, that gives us the angle. So in a way, I could solve for the time. But I would be solving for the time to give me an angle when the angle is pi over 2. So let's assume the angle is pi over 2. What's cosine of pi over 2? 0. 1 minus 0, 1. 1 times r is r, and that's what I'm expecting. It's another, moment. What about x? Well, we would have rolled down the road a quarter of the circumference. What's the circumference of a circle? Let's see if this is visible here. Circumference of a circle is pi times the diameter. So a quarter of the circumference would be pi times, the radius divided by 2, right? Because the radius is half the diameter. So that's what d would be. So, I'm trying to figure this out without using the formula. Now, that would be d, but we would be subtracting one radius. So in the case where the angle is pi over 2, we would have pi r over 2 minus 1 radius. So we could factor out an r, and we would get pi over 2 minus 1. That's what the x-coordinate had better be. It had better be that. Now, what was that again? That was where theta was pi over 2. So let's put that in this formula right here. If I make this pi over 2, what's sine of pi over 2? 1. 1 times r is r. What is this Vt? Let's see, Vt. If I multiply both sides by r right here, look, I would get r theta equals Vt. So Vt is, I just wrote it down, I lost track of it, is r theta, but theta in this case is pi over 2. So this is r pi over 2 minus r. So we'd have r pi over 2 minus r, which is r pi over 2 minus 1, which amazingly is what I've written down here. That's kind of because it's complex enough. Here's a couple interesting things I want to point out. This is not a proof that this is true, but this is sufficiently complex that the fact that worked, it gives you some level of confidence that it's true. Now, for those of you interested in physics, or you all should be sort of interested in physics, I'm sure you've all heard of string theory. There is absolutely zero physical proof that string theory is a true thing. And string theory currently does not provide an explanation for anything that we can experimentally work with. However, string theory, it does confirm what we already know to be true in terms of quantum mechanics and relativity. And it's so complicated, the fact that it agrees with what we already know to be true, it gives some people an overwhelming sense that somehow, well, this must be true. And I'll give you a famous, interesting quote from Einstein. Einstein was asked sometime just prior to, they were going to check one of the predictions of general relativity. I think it was 1918 or 1919, 1920. You can look it up. But it had to do with the orbit of Mercury. So Einstein's theory predicted that the orbit of Mercury would be slightly different than that which was predicted using Newtonian mechanics. And it turned out to be true. So it turned out relativity made a very interesting and accurate prediction mathematically of something that then was confirmed to be true. But somebody asked Einstein, what would you think if it turns out that your theory is not true? But what Einstein said is he said, I would feel sorry for God. Now, what he actually meant was this, because then he went on to explain it. The mathematics of general relativity, he felt, was so beautiful that if the universe didn't work that way, well, it should work that way because the math was so beautiful. And that's what had led him to come up with this theory, really, was the aesthetic, the poetic beauty of the mathematics. Well, and other things too. But that really was a factor in driving his development of relativity. And it turned out, so far, it works. It's amazing. If you look up gravity probe B, if you've never heard of this, Google gravity probe B, and you will find that we're still confirming things that Einstein's theory predicted. We haven't confirmed everything that's predicted. Or maybe you saw recently there was another example of gravitational lensing. There's been many examples of this, but still yet there's another one. And yet again, it confirmed the predictions of Einstein's theory. Now, one more thing, and then I'll stop the video. Look at these equations here. They're not very pleasant looking, and I think we can make them a little more pleasant now. What I did here was all intuitive, and it was natural. Again, it was like, I've never done this before. How would I do such a thing as this? Well, now maybe we can tidy things up a little bit. As a matter of fact, notice that this quantity right here, I want to erase some things. This quantity can all be replaced with theta. This can be replaced with theta. And certainly that would make this look a little nicer. Now, when I do that, I am changing the parameter. I'm changing the parameter from t to theta. You are absolutely allowed to do that. It is not written in stone what the parameter should be. To me, the natural parameter is, tell me how long the wheel, look at your watch and tell me how long the wheel's been rolling. And then I can tell you at what point on the cycloid we're at. Another would be to say, tell me how many angles the wheel has rotated through. And that's where the parameter would be theta. So from this one right here, we would get x equals vt minus r sine theta. But wait a second, we want to change parameters. So what is theta in terms of t? Or what is t in terms of theta? Look at this equation right here. Let's go to this equation right here. Let's solve for t. T is equal to multiply by r divided by v, and we'll get theta r divided by v. So I'm going to replace a t with that, theta r divided by v, and hey, that's kind of nice. Look, v's cancel each other out. We can factor the r out, and we get x equals r. What's left over there? Theta minus r sine theta. And I think that is the form of the equation that the book starts out with. So the book just, like, ready, set, go, gives you this, and then it derives it in a very slick, and I think somewhat non-intuitive way. So for me, from my point of view, this equation seems to come out of nowhere. It's like a rabbit trick. You pull the hat out of the rabbit, the hat out of the rabbit, the rabbit out of the hat, and you get that. So this is a different parametration. Oh my gosh, you could say that word. The book writes it, but this is a different way to write a parametric equation for this curve. And let's go ahead and do it with y down here too. With y, it's not so quite. We just swap in a theta there, so we would get y equals r 1 minus cosine theta. And so here's the parametric equations for the cycloid, where theta is the variable, and then these were where time was the variable. Now, certainly mathematically, look at these two right here. They're much easier. Much easier. Okay, so that's enough for this video. Keep an eye on announcements. I'll see you Wednesday. And if the sound doesn't work now, who can I blame except me? Nobody. I don't know. So, hey, remember, you have to work the problems in the book. Wednesday, well, you should. Wait, you don't have to. You should. But Wednesday, I'm going to give you your first actual assignment from the book to hand in for credit, which I know everybody's anxious for. So, see you Wednesday.